Hi everyone. Today I'm going to do an example of inferential statistics utilizing z-scores. Now, very quickly, let's think carefully again about what we're talking about when we use the term inferential statistics. No longer are we describing data, descriptive statistics. Rather, we're trying to make a probabilistic statement about a certain population based upon a subset of that population, what we call a sample. So if I take out a sample, what kind of statements can I make about the larger population based upon that sample? So let me give you a kind of a simplistic example of this. Let's imagine that I have a company with 500 managers, and let's say I happen to know that the population mean income for these managers is $51,800. Well, let's say I take some kind of a sample from these managers, and based upon the sample and based upon the population standard deviation, I know that the standard error is 730.3. What is the probability that my sample mean will be within $500 of the population mean? So let's think about what we're asking. We've got a bell curve, and in the middle we've got our mean of 51,800. All right? So what I'm trying to figure out is what's the probability that it's going to be within $500. So that would be 51,300 on this side, and then that's going to be 52,300. So the probability that if I pull out a sample, that sample mean is going to be within this particular territory. Well, recall z-scores, right? And so we want to convert each of these values to a particular z-score, and then we can figure out how to solve this particular problem. So that's forcing our mean, the standard normal probability distribution, forcing our mean to 0, and every other value is how many standard deviations away from the mean is it. So we've got the 51,300 minus our population mean, 51,800, and then we're dividing that by our standard error, 730.3. And then I've got 52,300 minus 51,800. Hopefully that's showing up well. And we're dividing that by our standard error as well. So if you do the math for this, you're going to get a negative 0.68. That is not showing up. Negative 0.68, and then this would be a positive 0.68. And then you'll have to go to the front of your book or anywhere there's a z-score table. If you can't find one, just Google it. They're all over the place. So if you look on the z-score table and you kind of matrix down, the z-score value for the positive 0.68 here is going to be 0.7517. And the z-score value for this is 0.2483. Now, again, what does that mean? It means that this value here, this 52,300, from here all the way over under this density curve, comprises over 75% of the entire curve, of the entire normal distribution. And from here all the way over comprises about 25%. So if I want to know what's in the middle, I'm simply going to take 0.7517 minus 0.2483, and you will get a value of 0.5034, or about 50%. So another way to interpret this, what's the probability that our sample mean will be within $500 of our population mean? It's about 50%. Now, if I wanted to tighten this a little bit, or if I wanted to increase my probability, would be a better way of saying it, how would I go about doing that? Well, if you said increase your sample size, you're right. Increasing your sample size lowers your standard error, which lowers the denominator in this value, and ultimately is going to give you a higher probability of your sample mean falling into this particular interval. And why is that in a more simplistic level? That's a technical level, but on a more simplistic level, because the larger your sample, the closer and closer and closer you're getting to approximating the real population. All right, this has been an example of using some inferential statistics. Thanks for your attention.